Okay, this video is about how can a function fail to be differentiable at a certain point? What makes that possible? So we want to just take a closer look at that. I've given you a worksheet to take notes on. This is mostly a note-taking video, I would say. So I have some blanks there for you to fill out. One says f prime of x is called the blank because it is derived from f of x, and the word that goes in that blank is derivative. It's called the derivative because it's derived from f of x. If you recall the earlier videos we looked at, how did we come up with a graph of f prime of x was looking at the slopes. We were sort of mapping the slopes of the graph all along the way. So that helps us answer the second blank. F prime of x is a graph of the slopes of f of x. So now I just want to show you different types of notations that you will come across with derivatives. You've been introduced to this one, f prime of x. This is notations of the derivative, okay? So we know f prime of x is associated with is the derivative of x. That's one way we can write a derivative. Here's another way we can write derivative. If it's written as y, we can just say y prime. That means the same thing. Here is something else that you probably haven't seen before unless you've had some calculus before. Dy dx. This stands for the change in y with respect to x. Dy dx is another way we can write it. Oh my goodness, my husband's coughing. The next thing we could write is d dx, the derivative of x of the function f. We can write that. You can also write, let's see what else we have. You could also write the derivative, a big D with respect to x of f. Or sometimes they don't write the x, it's just understood that it's with respect to x. So these are different notations of how you can write the derivative. So if you come across those, don't be confused. These are called this big D and this d dx. These are understood to be an operator, and this d is an operator, and it means it's a differentiator. I said that funny, it's a differentiator, and because the operation that it's saying is to take the derivative of. So that's what those mean. Let's see, the dy dx. This notation is called, it was developed by a person named Leibniz, and sometimes it's just referred to as Leibniz notation. So if you wanted to say, let's talk about at a specific value, you know how sometimes we'll say f prime of a, or we'll let a be a number. We'll say, let's find the derivative at x is 2, and we say it like that. If you were using this notation, then you would say, let's find dy dx at x equals to 2. That's how you would say at a specific point. Okay, so that's some different notations I just wanted to talk about with you guys. Now let's talk about how a function can fail to be differentiable. If you look below, there's a theorem I put on there, and this theorem is theorem 4 if you look at section 2.8 in the book. But it says if f is differentiable at a point A, then f is continuous at A. So here is one way it can fail to be differentiable at a point is it can be discontinuous. If something's discontinuous at a certain value, you cannot take the derivative at that value. So here's 3 ways. Let's just draw, here's a graph. Let's say it's coming in here. And then it hops up here. If this is point A, it fails to be differentiable at A because it's discontinuous. That's one way it can be discontinuous. Here's another way. Let's consider the absolute value graph, for instance. This would fail to be differentiable at x is 0. It fails at x is 0. Why? Because, remember, a derivative is this is continuous, so it's not because it's not continuous. This is continuous, but this fails to be differentiable at x is 0 because the tangent line slope coming from this direction is -1. And the tangent line slope coming from this direction is +1, and those are not the same number. So this fails to be differentiable because it doesn't have a tangent line basically at these values. So Anywhere you have a function that's got a sharp V or a cusp, something that's got a cusp like that, a cusp, or a kink, makes it, if a graph has that, it fails to be differentiable at that point. What happened here? It was discontinuous. This is what made it discontinuous, failed to be differentiable. And then the last way it can be, that a function can fail to be differentiable at a point is it could go vertical for a moment. So what if it goes here, here? Okay. So let's say we had some graph that did this. Right here, if this is A, do you see how this kind of went vertical? Well, what is the slope of a vertical line? It is undefined. And so if you have a vertical tangent line, if it goes vertical for a moment, then at that point that it goes vertical, you can't take the derivative at that point. So that's ways that a function can fail to be differentiable. Okay, now, the last thing I want to talk about on this is higher order derivatives. So this right here is known as the first derivative. F prime of x is the first derivative of x. You can have more than one. You can take a lot of derivatives. We could take a second derivative, and so that would look like this. Here's some first derivatives. F prime of x, also known as dy dx. This is a first derivative. Okay, here's a second derivative, f double prime of x. How would you write it in Leibniz notation? It would be d2y over dx2, the second derivative of y with respect to x. The third derivative, d3y dx3. And what if you just kept going down the line? What do you have? The nth derivative, fn of x. That would be dny or dx to the n. You can keep taking more and more derivatives. Now here's an example of something, what this means, okay? So let's consider the position function. S of t. Consider S of t, the position of a function. Well, if we took the derivative of this, take the first derivative of this, then S prime of t, what does this actually mean? This is the derivative, the change in the position with respect to time, the instantaneous change of position with respect to time, and that is known as velocity. This is known as velocity. Velocity. So this is v of t. So it turns out that S prime of t is equal to the velocity of t. Well, what if we took the derivative of the velocity? V prime of t. What does that equal to? Well, that would be the instantaneous change in the velocity with respect to time. And this is what we call acceleration. So here we go. Acceleration of a particle, of a vehicle, of something is equal to the first derivative of the velocity and the second derivative of the position of a function. So that is an example that we will be seeing of using the second derivative. All right.